All right, so for section 4.5 notes, I just wanted to quickly take a look or just kind of recall from chapter 2 that if n is a positive integer, we know this goes to 0 and this goes to 0. And just a reminder that the 1 does not have to be a 1. That just has to be any constant. So any constant, because a million divided by infinity is still going to be nothing, pretty much. Talked about the whole lottery ticket scenario. All right, and then just really quickly, a reminder on this one as well, that if we think about the e to the x graph, we know that there's an asymptote at 0 here, and so as I approach negative infinity, I'm going to approach that 0. All right, we also learned back in chapter 2, direct substitution, we learned that if we can, the first thing we do in something like this, if we're trying to find the limit, is we go ahead and just plug that number in. So we would have 2 squared minus 2, which would equal 4 minus 2, or 2. So we know that the limit for this function is 2. But now I'm going to ask you guys a new question. So looking at this next one, if I ask you to do direct substitution like we did before, we have infinity squared minus infinity, what do you think it equals? And this could get into quite the debate. It's kind of fun sometimes when we have these debates in class, and if you were in class, you will have had this that way. If you weren't in class, though, and had to watch this instead, you'll miss some of the discussions about who's to say whose infinity is bigger. We have countable and non-countable infinities, and it all kind of comes down to who ends up winning out in the long run. And so basically what happens is we consider this an indeterminate form, because really this is just infinity minus infinity. So is the answer 0? Is the answer infinity? You know, what is the answer on this one? And it's hard to tell, and we could graph it and we could definitely see what that answer is. But for right now, I want to talk about what we do when we get an indeterminate form. All right, so all of these are indeterminate forms, and you need to memorize these, because I'm going to give you kind of a shortcut for doing limits if we arrive at one of these forms. So basically, if you think about it, each of these we could debate, and that's what we will have done in class. So we will debate, well, who's to say? I mean, 0 divided by 0, anything divided by itself is 1. However, these are limits. So is the top getting to 0 quicker, or is the bottom getting to 0 quicker, or are they getting to 0 at the same time? Sorry, I should use the terms numerator and denominator. So same thing with the infinity divided by infinity. Who's growing faster? Because if the numerator is growing faster, we've already learned what happens. If the denominator is growing faster, we've already learned what happens. So what if they grow at the same rate? We also have already learned what happens with that, but we don't always know. And so each one of these is an indeterminate form. It's kind of like, I mean, if you go here to, here's one of my favorites because everybody says, oh, that's 1, duh. Okay, so 1 to any power, I agree, is 1. However, this is a limit. So if you take even these small, if you take a number just a little smaller than 1, and you take it to the infinite number power, or infinite power, it's actually going to go to 0, because if you multiply a fraction times itself over and over and over again, it just gets smaller and smaller and smaller. Whereas if you have just a tiny bit bigger than 1, say 1.0 to infinity 1, and you take that to the infinite power, it'll actually reach infinity. So these are all up for debate. If you want to have those debates and didn't get to have a chance in class to do that, come on in. I'd love to have those conversations with you. But for now, I'm going to teach you a shortcut when we get one of these rules. So plug it in, just like we had before, do direct substitution. If you arrive at one of these 7, then I'm going to show you what we can do. All right, and now this is all in your notes. Basically, what we do when we get one of the indeterminate forms is we can invoke L'Hopital's rule, or L'Hopital, depending on every one of my professors pronounced it differently. Not to be confused with L'Hospital. It is L'Hopital or L'Hopital. I usually say L'Hopital. So looking at this, we have, we're basically saying that if you have a rational function, and you get one of the indeterminate forms, then you can just derive the numerator and denominator separately. So there's no quotient rule invoked or anything like that or involved in this. It's just do each separately and then try again. All right, let's go ahead and do an example here. All right, so in doing these problems, the very first thing you need to do is figure out which of the indeterminate forms you are working with to verify that you can use L'Hopital's rule. So looking at this, if I go ahead and do direct substitution, I plug in 1, I know that ln, when it goes to 1, is 0 with direct substitution. And I also know that 1 minus 1 is 0. So I have an indeterminate form. All right, so every time I use L'Hopital's rule, I always like to put a little h over the equal sign so that I can communicate that I'm not doing something illegal. I do know what I'm doing. I'm not forgetting the quotient rule. So I put a little h, and then I know that that's what I'm doing. So my derivative of my numerator is 1 over x. The derivative of the denominator is 1. That simplifies to 1 over x. And now I can go ahead and do direct substitution again. So now if I put 1 in, I get 1 over 1, and therefore I know that the limit is 1. Kind of slick, right? All right, let's look at another example. All right, so again, very first step, plug it in and see what you get. Well, I know as e to the x approaches infinity, I know that it goes to infinity, and I also know that that x squared as it approaches infinity goes to infinity. All right, so we're going to go ahead and put our little h over our equal sign to indicate that we're doing L'Hopital's rule. And so I would have the derivative of the numerator is e to the x, the derivative of the denominator is 2x. So now I go ahead and I plug in infinity again. So just like before, our numerator goes to infinity, and our denominator, well, it's a linear function, it's positive, so it's increasing, it's also going to approach infinity. So you notice we get another indeterminate form. However, that doesn't mean we're done. It just means that we can apply L'Hopital's rule again. So I'm going to apply L'Hopital's rule now to this function. So I would have e to the x over 2. And now I'm going to do direct substitution again, and I would get infinity over 2, and we know that half of infinity is the same as infinity, so therefore this limit is infinity. All right, now moving on to example 3. Our issue with example 3 is that we don't have a rational function. But again, we haven't even tested it yet to see if it's an indeterminate form. So I'm going to go ahead and plug in 0, and I know that when I approach 0 from the right of the function of x, y equals x, that I go to 0. And then if I plug 0 in, I know that the ln x graph, just to remind you, the log function looks like this. So as I approach 0, coming from the right, I go to negative infinity. And now that is one of the indeterminate forms. So I can use L'Hopital's rule. The only problem is, again, I don't have a rational function. So we turn this into one. We simply are going to rewrite this as the limit as x goes to 0 from the right of ln x over x to the negative 1. And now maybe you ask, why did I choose to move that one down? Sometimes I don't always know. I just have to start and see what happens. So in looking at this, it might work, it may not, but it made sense to move that one down because it was much easier than having to apply ln x to the negative 1. So I'm going to go ahead and use L'Hopital's rule now, which would mean I'm going to take the derivative of the numerator over the derivative of the denominator. Okay, so I'm not quite ready to plug 0 in just yet. Instead, I'm going to simplify this a little bit first. So I know that this is 1 over x times negative x squared, because really the x to the negative 2 means it should be up in the numerator. All right, so with that being stated, or that being rearranged that way, I know that it's going to be negative x when I simplify it down. So now if I go ahead and plug 0 into just negative x, that's completely legal, and I get 0. So the limit of this function is 0. Now for our next example, we're actually going to come back to that. I'm going to use that idea again. So don't forget that the limit of this function goes to 0, and you'll see why in our next example here. All right, so again, this next one, the first thing we want to do is figure out what the indeterminate form is. When I look at this one, all right, and if we do direct substitution, we get 0 to the 0, which we know is an indeterminate form. Now, just as in the last problem, we need to turn this into a rational function. However, right now we have x as a base and x as an exponent, so we probably need to somehow get logs in there. But we only have an expression. We just have find the limit. We don't have an actual equation. In order to apply logs, we have to be able to do it to both sides. So the very first thing I'm going to do is I'm going to go ahead and make this into an equation. And I'm going to simply do this by using substitution. I'm going to say that y equals x to the x. All right, well then if y equals x to the x, I have limit as x goes to 0 from the right of y will equal limit as x goes to 0 from the right of x to the x. All right, now that I have an equation, I can go ahead and apply the natural log to both sides. So I have limit as x goes to 0 from the right, ln y, and I have limit as x goes to 0 from the right, x ln x. All right, remember in the last example I said I wanted you to keep in mind that we found that it went to 0? Well, hopefully you recognize this from our previous example. That's what we just found the limit for. And we determined that that limit for that goes to 0. So I can go ahead and replace the right side with 0. All right, now if I want to solve this for y, because that's what my whole point was, I want to know for x to the x, I need to get rid of the natural log that I used. So I'm going to go ahead and I'm going to apply e to both sides. So if I apply e to the side, I get y, and if I apply e to the other side, I get e to the 0. So in other words, and we know e to the 0 equals 1. So therefore, limit as x goes to 0 from the right of y equals 1. And since y equals x to the x, we know the limit as x goes to 0 from the right of x to the x also must equal 1.